Hello. Today we're going to talk about intermolecular or interparticle forces and is a little overview what we're going to do here today. I hope you remember from previous units what intermolecular forces are. So they are the forces between molecules. So covalent bond, as you can see here, is its estimated strength, estimated energy is much higher than what we call intermolecular forces. So you've got here ion dipole, which is very rare, rarely talked about in AP, hydrogen bond, dipole, dipole, and dispersion is London dispersion for a small molecule. So this is just an estimated energy of these bonds that you can see here. But we need to say it right here that ionic bond is stronger than all of these, and then metallic bond goes at the top. Why am I mentioning these two? Well, covalent bond is not something that is considered an intermolecular bond, but ionic and metallic bonds are. Why? Because mostly the strength of the intermolecular bond is connected with melting and boiling points. To boil something, you break certain types of bonds. Basically, you break all the bonds except for the covalent bond. So, in order to boil something, you need to break metallic bond if it's a metal, right? Ionic bond if it's a lattice, ion dipole, hydrogen bond, dipole, dipole, and dispersion. But boiling does not break the covalent bond. That's why covalent bond is the only bond that is actually not considered intermolecular. So it's given here as a comparison because it has such a high energy, and then uh, kind of explains why it doesn't break. There's a more difficult, more complex, and more correct explanation, but that is not important right now. Now, London dispersion forces, as you've seen, are the weakest, and you will see them often, especially if you go to college and study something related to chemistry, that they're often called induced dipole forces. Why induced dipole? Well, induced dipole is a temporary dipole that happens probably, I mean, not probably, for sure by chance. So look at this. There's an example of helium. So helium's got two protons in the nucleus, two neutrons, and it's got two electrons. And the electrons can move in this space here. They just move randomly. But there's only two of them. And at one point in time, by pure chance, these two electrons will end up being on the same side, on the right side of this space where they can move, right? And then that side will become partially negative, and the other side will become partially positive. And then this other atom that is close by will get influenced by this. So the electrons in this atom will go to this side because they will get attracted by this delta plus, by this positive side of the other atom. And then you will get this attraction. This red arrow is the attraction between the two induced dipole, which is called the London dispersion force. You can see that all these forces, except for maybe hydrogen bonding, are electrostatic. They're Coulomb forces. They're attractions between different pluses and minuses. But as you can see here, this separation of plus and minus here is pretty, it's just temporary. It's a pretty weak separation, which means that we can use this to explain why London dispersion are usually the weakest forces. And not always, you will see there are exceptions. And here you've got some things which you can use to rank if they ask you to compare two atoms and two molecules and tell them which one has stronger London dispersion. So the first thing that you should look at is which one has more electrons. What has more electrons usually has a stronger London dispersion and therefore a higher boiling point. For example, I know oxygen O2, oxygen molecule has a stronger, higher boiling point than helium because helium only got two electrons and two electrons, and O2 and O2 they have 16 and 16 electrons. So if there are more electrons, there is just a bigger chance that one side of the atom will become more negative and then the other side will become positive. So there's a bigger, higher chance of inducing dipoles. The second thing that you should consider is the contact area. Uh, Basically, molecules and atoms which are bigger, they've got more space for electrons to move, and they also got more area, more surface, which can be approached by the other atoms or molecules. So that means that they have a higher chance of inducing a dipole. And then you also should consider pi bonding. It's better to say delocalization because if you have double, triple bonds or resonance, that means that the electrons in those bonds are able to move more freely. So that means that the dipole will be induced more easily. However, in most questions and in most realistic examples, the number of electrons will win here. The number of electrons and contact area basically in tandem, let's say. But mostly you should first look at the number of electrons here. Now, dipole. You learned about polar molecules in Unit 2, so here I'm just kind of reviewing that. So if you've got a polar molecule such as HCl, so the electronegativity difference is enough for partial separation of charges. So Cl is partially negative and H is partially positive. And then if that gets close to another atom of the same type, dipole, or what I like to call DD bond, will get formed between these two dipoles. Please bear in mind that I just put this red arrow here to show you. In chemistry, we do not mark the dipole bond with the red arrow. The red arrow is we just basically put the two molecules or atoms close by. Actual atoms cannot be dipoles, so we just put two dipole molecules close by, and we just turn the delta plus to the delta minus, and that's how we mark it. We don't put this arrow. I just put it here for you to show you some clarity. And then there's another example here. So I mean, it doesn't only exist between the same molecule and it can exist between water and HCl2. So why is dipole stronger than London dispersion? Well, London dispersion is basically a temporary dipole, so it's just going to disappear in a second. So of course, when you consider a large number of molecules, dipole exists always, so it's just going to create a higher boiling point, and therefore is going to be a stronger intermolecular force. Now, hydrogen bond, this time, these broken lines are an actual official way to mark a hydrogen bond. Hydrogen bond is the only one that has this type of official way to mark it. And hydrogen bond is special in many ways. It's still not proven, or even it's best to say, still isn't really discovered why it's there. There is some indication that it also depends on it's also Coulomb force in nature, but we don't really know, and that's not something that they will ask you in AP Chem or even in college for that matter. But when does hydrogen bond happen? When it happens, if in one molecule you've got oxygen covalently bonded with hydrogen, nitrogen covalently bonded with hydrogen, or fluorine covalently bonded with hydrogen. And in the other molecule, you've got either of these. So oxygen, nitrogen, or fluorine, they can be bonded with something else. So as you can see, it happens between two of the same molecules, two water molecules, or it can happen between methanol and ammonia. So please bear in mind again that a lot of mistakes happen with this, so it's really important to remember this rule. And also that in some books you'll see that Cl bonded covalent with H can also form a hydrogen bond, but that's not considered so in AP curriculum. So we only look at these here. And I gave you this to show you that watch this shape here. This is like a half an arrow. It's missing one side, right? An arrow is often used to mark, to point to a negative side of a dipole. So if you've got an arrow like this or half an arrow, so the direction where the arrow is pointing is basically delta minus. So you will sometimes just see that when instead of delta plus and delta minus like this. And yeah, here you have what we today consider the best explanation of why the hydrogen bonding happens. Uh, it's still not clear, and we just know that it's one of the strongest intermolecular bonds, so stronger than London dispersion, stronger than dipole dipole. Ion dipole. Ion dipole is not very often given in questions. Simply, it's an attraction between an ion and a dipole. It serves a lot to explain why dissolving happens. So you can see here, if you have a positive ion and you have a dipole close by, then the delta minus side of the dipole would just get uh, attracted. Again, this is Coulombic in nature, and again, this arrow is not really how you should represent it. Again, it's there just for clarity. Uh, these forces are stronger than hydrogen bond, but these forces are also very easily influenced by other stuff, and that's why they're not very often given in questions, except when they're explaining dissolving. So you have NaCl, NaCl is a lattice. Why does the lattice break? Well, because these are really strong. So when you have a lot of water that surrounds the pluses and the minuses in the lattice, then they can get dissolved. And one more time, you've got rankings here. You can check this out. I'll leave the PPT. You can use it as a reminder. Uh, yeah, so like dissolves the like. Again, I want to repeat that. You will see when we discuss dissolving in more detail, it depends a lot on these intermolecular interactions, but in many ways which are not really something that is always logical. And also, you've got this here, dipole induced dipole. I mean, that can exist. You got a dipole, and next to it, you can have something that has no polarity, but when it gets close to a dipole, then the if the negative side of the dipole gets close to the non-dipole, then the electrons are just going to run away to the other side, and then you've got dipole-induced dipole interaction. Again, this is a bit more difficult, not often given in AP curriculum, but you will see why I showed you this a bit later. And here we have which physical properties are influenced by intermolecular forces. So mostly in AP curriculum, they'll ask you about boiling points and melting points, and even then, mostly about boiling points. So if all of these are very logical, if you just think about what's happening. So why is boiling point higher if intermolecular forces are stronger? Well, you need to break all the. You need to basically make particles able to move fast and independent of each other in order for them to become gas. So that means you need to break all the bonds except for the covalent bonds, because if you don't break the covalent bonds, you can still be vapor because molecules are still able to, particles able to go away. And then viscosity, surface tension, vapor pressure. I mean, again, it's very easy to just logic your way out of these questions. For example, vapor pressure. What is vapor pressure? The pressure of vapor when you're boiling something solid, right? And you got vapor, or when you just have vapor in a container. If intermolecular forces between the particles of gas in that container are higher, there's going to be less pressure because particles are going to hit the wall of the container less than if you had less intermolecular forces going to hit the container more pressure, right? So I mean, you will see. We'll discuss this in this unit much more. Now let's check out some examples. So for each substance, name the strongest intermolecular force present: chlorine, HCl, and methanol. I advise you to always name all the forces and then just circle the strongest. But I mean, it's the question. And as you can see, Chlorine has only London dispersion, obviously, because there's no dipole. HCl is a dipole, but also has London dispersion, right? But I mean, the strongest force is dipole-dipole. And CH3OH has an O covalently bond with H present, which means it also has a hydrogen bond, which in this case will be the strongest interaction. Now, rank the following from the lowest to highest boiling point. So we've got argon, methane, ammonia, and NAF. Oh, this question has two things I wanted to talk to you about. So check this out. Argon and methane both have only dispersion, only London dispersion. But argon has more electrons than CH4. And that's why it has stronger intermolecular forces than CH4. This might sound counterintuitive. So argon has more electrons, but CH4 is probably bigger. However, as I told you, most of the time the number of electrons win. And then you've got NH3, which has hydrogen bonding. It's also got dipole-dipole and London dispersion, but again, hydrogen bonding is dominant, and the other interactions are not significant compared to hydrogen bonding. And then you've got NAF, which is ionic. So when talking about the boiling point, again, you need to consider also ionic and metallic, because if you were to boil something, those two things also need to be broken. So NAF has actually the highest boiling point, right? Now you've got propane and acetaldehyde, and they have very similar molar mass. But also, acetaldehyde boils much higher. So acetaldehyde must have stronger intermolecular forces. So let's check out which one has which. And here I think I drew it. I want to torture you some more with my drawing. So as you can see, the first one only has London dispersion, LD, because it's got no dipole, it's got no oxygen, nitrogen, and fluorine covalently bonded with hydrogen, so no hydrogen bond. However, this one has London dispersion and dipole-dipole. I like to call it DD, right? So also, please pay attention that here I drew this C like this with the angle of 120 because it's important when considering whether something is a dipole or not to draw the Lewis formula in such a way to approximate the actual angle that we did in Unit 2. So, because sometimes it might seem like it's not a dipole, but it actually is because it depends on geometry. And yeah, here they just explained it in a more structured way. I guess I like drawing; helps me much more than this. Now, HCl is polar. Hydrogen iodide is only weakly polar. Yet HI boils higher than HCl. So HCl has a stronger dipole because obviously Cl has a higher electronegativity than I. However, HI has a much higher boiling point. I mean, it's a dead giveaway this week when dispersion beats polarity. So this is one of those cases when I was talking to you about that dipole is in general stronger than London dispersion, but that's not always the case. Here you've got I, which has way more electrons than chlorine and a much bigger size than chlorine. So this is specific of group 7 and very specific iodine. Even I2 has so much of a higher boiling point than Cl2 that it's not even comparable. So I ask you to remember this example. So 99.9% of the time, dipole is going to be stronger than London dispersion. But with iodine, that's often not the case. Not the case in examples with iodine. And This is one of the only examples of this. So just remember it. It might be useful, right? Oh, we don't know. So three compounds around 46 grams per mole. And again, you've got three similar things. So dimethyl ether, ethanol, and propane, and rank the boiling points. Why are they giving you here molar masses? Because if something's got this molar mass, that means most likely it's got similar number of electrons, right? Why? Because I mean, molar mass depends on the number of protons and neutrons, but as what has more protons, more neutrons, most likely have more electrons. So that's what they're giving you. That's what they're giving you this. Uh, Now again, I drew it. So as you can see, propane again only has London dispersion, while dimethyl ether has London dispersion, but also it's a dipole. And here you can see why it's important to draw it correctly, because I could have drawn O and then CH3, and then it's not going to look like a dipole. I mean, it's going to look like something, but it's going to look weird. But remember that oxygen has two free electron pairs. So it's basically tetrahedral, where you have two electron pairs and two bonds here. So it's very clearly a, a dipole. And then you've got what is this, ethanol, and ethanol obviously has a dipole, has LD because everything has one dispersion, but also has a hydrogen bond because it has O covalently bonded with H. And yeah, here is a more structured explanation. Check it out. Potassium chloride dissolves in water readily, but not in hexane, a nonpolar solvent. Name the force responsible for dissolving it in water and explain why hexane fails. And we discussed all this, so it has a. I mean, this is not that much of a good picture. So KCl is ionic, so there's going to be a strong ion dipole interaction between the dipoles of water and uh, K plus and on one side and Cl minus on the other side. While hexane is not polar, something that is not polar is not very likely to dissolve a polar thing, and even less an ionic thing. So non-polar things usually dissolve other non-polar things. As we said, like dissolves the like. And number seven, oxygen gas is non-polar, yet a small amount dissolves in water. So this is kind of against what I just said. So you got oxygen, which is non-polar, and you got water, which is polar. There's still very small amount of oxygen dissolving in water. I mean, the fish can breathe, right? So what does that happen? Why does that happen? Well, remember induced dipole. So water is a dipole, and when it gets close to oxygen, which is not a dipole, it induces a dipole. So you can see this negative side of water gets close to oxygen, which means that all the electrons in oxygen are trying to get away from it, creating an induced dipole. And this is the dipole induced dipole force. Again, not a very common question. This is a very difficult question, actually. Uh, Now, deciding which statements are true and false is something I really like to do because it covers a lot of content. So, uh, the difference between intermolecular force and chemical bonds. Boiling a molecular liquid breaks its covalent bonds. Does it? What do we say about boiling? Let me just show you since this is a very long video. So, boiling doesn't break covalent forces. Everything has London dispersion. Anything has electrons, and everything has electrons, right? All the matter, anyways. A polar molecule always boils higher than any nonpolar. We've proven that's not correct, right? With HI is much less polar, and you can have like I2, which is completely nonpolar, but still has higher boiling point, right? Hydrogen bonding can occur in a molecule that only has CH bonds. No. Okay, so Remember these. Try to do the questions and let me know if you need help. And off I go.